Chapter 5.
What's that left pencil?
The second line again.
Okay, let's look here. Whose notes are good? Okay, let's look at yours. What's the last problem that we started? 2 blocks on the 2 equals. Not that one. No.
This one? This one?
It's already a bad sign. No,
How about this one? Right here?
Okay, 0 out of 2. That's not a good. No, I'm random. That's the whole thing.
Ah, okay.
Yeah. If I only go to the people that always have it, what's the point?
I know. This is the first time I have it. I drew it real nice too, though.
Yeah, but how about the question and how far did you go along?
Never mind. Don't pick me.
Okay, 0 out of 3. Wow. Man. Woo. No good so far. No bueno. Well, this one also no good. We've done some of it already. 0 out of 4. We already did some stuff.
Right out the question.
Random. Patrick, let's look. Huh? How much did, no, that problem, how much did we do so far? No, I mean from that, for that problem, how much did we, no, I know you will have it, random. How much did we do? No, 0 out of 5. Okay, finally, on the 6th one. 1 out of 6. So I guess we need a certain class, guys, on note taking. Before taking physics, forget that, no taking physics. A whole semester on note taking. Okay. Okay, so now let's see here, this is 16 kilograms. So does the system, the question was, is the system going to move? If yes, what is its acceleration? If not, then we know that it's not gonna move. So we calculated Fs max, the maximum friction on this guy, right? And we got here 0.16 times 49 cosine of 40. We got 6.00 newtons, right? And Fs prime max, these ones we call them prime on this side. That's equal to 0.45 times, and then the weight of that, we made it heavy, so that 16 times 9.8, 156.8 cosine of 35. 57.8. I think at the end I made a wrong, I think I said wrong. I said the system will move.
We
Right.
adjusted something because it wasn't moving and we redid it again.
Yeah, we did it again
I
with six,
think
because
that-
at first I had 6 kilograms.
Yeah, and you added
then
the
I
one.
changed it to 16, but it still doesn't move. I was wrong. I said it will move because the sum of these two forces is
58.
63.8, right?
On my notes, it said 58.45.
No, that's the difference between
Oh,
their.
I'm sorry.
Yeah.
Yeah, sorry.
So remember, you break these weights into their.
Yeah.
Because they're competing against each other. So
Yeah.
then this guy is the downward component of the weight of this. So that one is 49 sine of 40, which is 31.49. And then this one is 156.8 sine of 35. Now in your notes, who gave me this? It's not complete. You're not showing how you got the 84 and the 31. No good. So that's a half. Is 1.5 out of 6. I have one notes, but not complete. Right? So you got to show how you're getting the downward component of the weight of that, how you're getting the downward component of that. This one comes out to be what? 86 point, what is it? 49? Is that it?
89.94.
Yeah.
Oh, 89.94. Okay, now if I subtract that, 89.94 minus 31.49, see, it still will not move. 13, no, 15. This becomes 8, 8, 4, 8, 58. So you see what's happening here is that the reason the system can move, if it ever will move, is that their weights are fighting against each other. If there's no friction, of course the system will move. We don't even have to do all of this. But because of friction, the friction here will oppose that motion, right? And then the friction here will oppose it. And what we're trying to do is, hold on, this one is, oh no, this friction is downhill, right?
Yeah, going down.
It's going down. So this friction at maximum can be 6 newtons. That's the maximum it can be. And this friction can be 57.8. So together they can exert a total sum of 63 newtons. Well, that's more than the difference of these two weights, right? 58 is less than 63. So the system doesn't move. I don't know if that's a happy face or a sad face. Okay, so if it doesn't move, can we find out what the friction force on each one is individually? So the question can say, A, if does the system move? System move. Yes or no? And once you determine if it's yes or no, then B can say, if no, what is the friction force on each block? And then if yes, what is the acceleration of the system? Right? So in our case, we know it's a no. So the answer is a no, right? So what is the friction force on each block?
Set up the equation.
Huh?
It'd just be the force going down each.
In other words, does the friction here, this one's 6 newtons, it seems like that one probably reaches its max, right? Earlier than this guy does, right? So, in other words, just simply by equations, you have the tension in the string, right? So you have T is equal to 6 plus this guy, right? So let's assume this one reaches its maximum, this friction. Assume it. I believe it will, because 6 newtons, it will reach it. This one will reach its maximum before this one ever does, right? So then what's going to happen is T plus 6 is equal to what? Sorry, it's not T plus 6. It's T is equal to what?
6 plus.
So these kind of problems is really good. It's all visual, you see. You can see one force is up, so that one has to equal this plus this. Both of these are trying to drag the system down the incline, right? So it's 6 plus 31.49. Right? And then so T is equal to 37.49 newtons. So in other words, what happens is that this block, as soon as you put it here and you connect it with a string, this block wants to go downhill. This guy is trying to make this one go up, and then the friction goes up to 6 and says, I give up already. I can't be larger than 6, right? And then the friction here says, I'll come and help you, right? Because this friction is weak, you see? And then, so now what's this friction gonna equal? Fs prime, we can call it. It's not gonna equal to its max, because it doesn't need to equal to its maximum,
So it's
right? So you say T plus Fs prime,
is equal to down.
right? So this plus this equals this, right? Very visual, just look at it visually. T plus this equals 89.74. So the T that you got, you put it here. Then you subtract this minus this, right? And if that's equal to less than its maximum is 57. That's another way of showing that the system doesn't move, right? So 37 you subtract from this.
Where do you get the 89.7?
The 89, this guy, the weight of this.
You're gonna have 94?
89 point, what was it?
94?
94?
Yeah,
I did that on purpose. My handwriting wasn't good, and so I read my handwriting wrong. Right? Do you guys ever do that? Exactly. I'm just trying to model what you guys do. It's always on purpose. Okay, so you have 15, 8, 4, 2, is that 2? Yes, and then 5. Okay, is that good? So in other words, the friction here only has to equal 52 newtons in order to prevent this guy from moving and also helping the other one not to move, right? So can it be 52? Yeah, because we found out that it can be as much as 57, right? So it can be 52. So this only tells you the maximum possible that static friction can be, you see? So now this proves to you that the system doesn't move for sure. Fs prime is 52, Fs is 6, and then the tension, in case the problem asks about the tension is 37.
Question.
Yes.
So if you were to use like M and M, could you find an inequality of like the masses of when the system would move or no?
A general inequality?
Yeah, like
Yeah,
in
of
the-
course. Yeah. The big M and little m?
Yeah.
Yep. See, this one also not only it's light, but it also has very little friction. Okay. Okay. Now part C. What if I add 4 more kilograms here on the left side? You think the system is going to move?
Maybe.
harmony.
I think so, yeah, because this barely moved. Yeah, this one is definitely, I'm pretty sure it will move. So if the 16 kilogram changes to 20 kilogram, what is the acceleration of the system? And the tension in the string. Okay? So now redo it. To get it started, see if you can get it started. I made the 16 into 20. Well, before finding out, before getting the A and the T, you have to first prove that the system is gonna move, right? I mean, just because I said so doesn't mean it will. So how would you check? You have to do exactly what we did all over again, right? So how would you check if the system does move? Well, recalculate the weight of this, right? 20 times 9.8, that's gonna be 196. And then this is gonna be 196 cosine 35. So redo this thing, right? Redo this thing. 196 sine 35, 196 cos 35, right? So you do the 196 cos, 196 sine, then what do? You redo this guy, right? Fs max. This one stays the same, but this one changes to 196 cos. So you try to figure out what the maximum friction, static friction is, right? Under 20 kilograms. So 196.
That's Fs max, not F prime.
Which one?
Isn't that for the right side?
Which one? This one?
Yeah.
6 newtons? Yeah, that one doesn't change.
Yeah, that's what I'm saying.
But you have to figure this one
That
out.
one out, yeah.
Yeah, exactly.
I thought you were doing the other one.
So this one is gonna be the 160, right? 0.55 times 0.45. So 72.25. So together 78.25. The two frictions together give you 78, right? Then you figure out this one is 112.42. 112.42 minus 31.49. So the difference of their rates. Oh, barely. Huh? Right? So together, the two frictions can only exert 78 newtons of force, but the difference of their weights is 80. It will move. Right? So it's greater than 78.25. So the system moves. Yeah? You guys see the logic? If the two competing forces, you subtract, you get 80, but together the friction is 72, the maximum friction is 72, and then the maximum friction of this is 6. So together it can only give you 78 newtons of support. So system moves. See? So now if the system moves, what will happen? Which direction will it move? Well, then this guy will move down, this tension will be up, and then what's going to happen? The friction force reverts to kinetic friction, right? Once the system moves. So we change this to kinetic, which is mu k prime n prime. And then this one goes, and then this friction also changes to kinetic, right? Mu k n. Okay? So now what happens? This guy accelerates down the incline, this guy accelerates up the incline. So now it's just going to be visual. Look at the visually. 112.42 minus what? Minus the tension, minus the friction, but kinetic friction now. So what is that? 0.3, right? 0.3 times the normal force, which is what? The normal force is going to be 160.55, right? Is equal to the mass of the block times its acceleration. So the downward force of the weight minus the tension minus the kinetic friction is equal to mass times acceleration, right? And then for this one now, the tension wins because the net acceleration is up. So now you do T minus the downward weight, 31.49, minus the kinetic friction, which is mu k n. So the mu k is 0.10. Times the n of that is what? The n of that was 49 cos 40, right? 49 cos 40. Which one was what equal to? Well, let's just write it 49 cos 40. That's equal to what? 5a. So it's always the winning force minus the two losing forces. So this force is winning, and these two forces are competing against. So the winning force minus the two losing forces equals the mass times acceleration, and then the winning force minus the two losing forces. Okay, so then you can then add these two equations. When you add the left, make sure to add the right. Right, so then you have here 112.42. Negative t plus t cancels. and then you add the right side is 25A.
Not the 31.
Which one?
The 31.1.
31.
Yeah, like on the where you added the equations, I mean.
That's 31. Oh, that's the downward component of the weight. Did I forget that?
On the
Negative
bottom.
TT, negative 31, negative. Oh, you have three things to subtract, right? Again, I did on purpose. Because often students will forget that too. Right? Can't forget that. Now, the two competing forces, the weights, and then the two frictions. So that means they both accelerate at that rate of 1.16 meter per second squared. And then once you get that, you can put it back into here to calculate the tension, right? Into either of these two equations. I can put it here, then add everything here to that side, and then calculate for the tension. What was the tension in the earlier case? 37 newtons, right? Yeah, so when we added more weight on them, made it from 16 to 20, the tension in the string should get tighter, right? Yeah, that makes sense. When it was 16 kilograms, it was 37 newtons of tension. Okay? So tension is sort of the measure of the stretching of the string, how much you're stretching it, right? Okay, yeah, look at that again, review that. I'll give you a minute or so. Review it, make sure you can understand.
So like in the beginning when you're comparing the sums of the friction with the tension, or like with the effective weight to figure out who's not, it's because like every point on the string has to be moving in the same way, right? And that's why you can do it effective. Because they have different angles, but every point on the string has to.
For the acceleration to be the same?
Yeah.
Yeah.
I think that is
Yeah.
right there.
You're understanding? And look at that, look at everything.
It's just
phrase you kept saying was it's the winning force minus the 2 losing forces equals acceleration. Is that what you said?
Winning force minus the 2 losing forces. Yeah, minus any losing force that you have. Yeah.
Equals acceleration.
Yeah.
I just never seen like acceleration kind of used kind of like this, like almost like a variable. We can just
Because the Newton's law is saying sum of the forces on an object is equal to the mass times its net
Yeah.
acceleration. So
Yeah.
you have, usually you'll have some object, you'll have some force like this, some force like
Right.
this, some force like this, let's say. Let's say we know that it's accelerating that way. Then we do this force plus that force, component of that force, minus this force. So F1 plus F2 cos theta minus F3 is equal to MA. Winning forces minus losing forces.
no, I get the math on it.
Right?
I've
And then
never-
if there's a string here with a pulley, right? Then what happens? F3 becomes the tension in the string. Right? And then you have tension. Then you have the weight of this guy. Right? So if this is accelerating this way, these two are beating the tension, right? And let's call this M1A. And then which direction is this accelerating? If that's accelerating to the right, this guy's accelerating up, right? So then tension is beating this
Yeah.
guy. So then T minus M2G is M2A. Then you add these two. There's your possible test question. You know?
Like, I'm just used to like working out on force tables, not like with the short. I've never seen it like on the shorthand kind of that way, almost like it's a variable.
Yeah.
I mean, I get it. It's just I've never like
Yeah.
when I was writing it down right now, it confused me for a second. I was like, wait, what the hell is that?
Almost as if A is a variable.
Variable,
Yeah,
yeah.
it is.
Like, it
it's
is.
It's an unknown variable.
I
Yeah.
just, I'm used to seeing it in a force table and separated, not like just in a straight equation like this.
Mm.
But I get it. Though.
Yeah. Okay, how about this one? This is kind of like that block problem that we had before with the block, and then that one had a pulley and another block, but one is just hanging there, freely hanging. I say, wait a minute, if it's freely hanging, isn't it gonna fall, right? Yeah, it will fall, but I'm gonna ask a question. I'm gonna say, what is F min required
Make it not forward.
for the 2 kilogram block? What is the F minimum? The minimum force required that you should push this one with, so that for the 2 kilogram block to stay stationary. Can you do that? Can you possibly push the 10 kilogram with enough of a force? And the answer is yes, yeah. It's almost like Spider-Man in the movie where he's like in front of the train and the train is pushing him, right? But then he had the webs, he threw it with the buildings and he stopped the train, right? This is Spider-Man. Which one was that? The first one?
Second one.
With the spider webs. buildings.
Spider-Man.
Right.
He doesn't just-
He stopped it before it went over the track. Right, so then B we can say
That's two. Two.
so if F equals 5 newtons less, if you exert the 5 newtons less force than that, what acceleration will the block slide down the block? That would be the 2 kilogram block slide down the 10 kilogram block. Okay? And then the same way for the other one. So how do we find this minimum force required? So, of course, I have to move, exert enough of force to beat the static friction, right? So it has to be moving. So that means we don't even need to know the static coefficient of friction. It's just extra information. So this guy is gonna be F, then you're gonna have here what? Mu K prime, N prime, then you're gonna have here N prime, then you're gonna have the weight, which is 10 times 9.8, which is 98, right? Then you're gonna have then you're gonna have here the 2 kilogram. Now let's focus a little bit on the forces on the 2 kilogram. What's happening to the 2 kilogram? There's a force pushing that. Remember the internal force between the blocks? We called it P before, for the other problem. We'll call it P again now. P. Then there is a friction force up, right? Preventing it from sliding down. So what's the friction force? Well, if it's not sliding, the maximum friction force is mu s n, right? Mu s n. You know what? We could just call this one n if we want. Instead of p, call it n, because that's the normal force between the two blocks. It's just weird that it's horizontal, but it could be, you know. So it's this guy's pushing on this guy with a force of n. Then the maximum friction that's allowed that hold it up is mu s n, and then you got its weight, which is 2 times 9.8, 19.6. Is there any other forces on that block? No, that's it, right?
Doesn't it exert a force on the...
Yeah, so now we need to go back. So now we need to say, okay, if those are all the forces on the 2 kilogram, does this have any Newton's third law of action reaction? What are the forces on the 10 kilogram due to this? Well, this guy is pushing this one this way, and so this guy has to push this guy back with N. Always, every force have to have a reaction. So there's an N here. Then there's a mu K prime N prime, which is this of N prime. But then there's another one that's kind of hard to catch. The friction force on this guy due to the 10 kilogram, right? So this guy is exerting a force on this guy this way, mu S N. Therefore, this guy has to exert a force on this guy this way. That's easy to miss. So there's a action-reaction pair. Friction also comes in as a pair. right? If this one supports this one by pushing it up, this one supports this one by pushing it down, right? So there's a force here on this guy, which is down, which is mu, it's just the same thing as this guy, mu s n.
Is that only present for static friction or?
No, kinetic friction too. Newton's law, third law, always, anything. N, mu s n, mu k n.
So would there be a mu kn on the floor, but we don't consider it to this one?
Yeah, if it's sliding, we're gonna have to do that, yeah. So now, let's do the forces on this guy. We know it's gonna accelerate to the right, right? So n is equal to 2a. The acceleration is this way. And then mu s n has to equal 19.6, right? I think from there we can already calculate what the, and then mu s we already know is a half, right? So we could say here 0.5, n is equal to 2a. So that means the acceleration is 19.6. That means I have to exert such a force, strong force on this system so that the whole system accelerates to the right with an acceleration of 19.6 meters per second squared. That's very fast acceleration. And if A is 19.6, that means the normal force is what? 2A. And so it has to be 39.2 newtons. All right, so then the normal force on this guy is 39.2 newtons. The acceleration of this guy is 19.6 meters per second squared. Now I can go and analyze what's happening to the 10 kilogram. So here's the 10 kilogram. You got the force F pushing this way. You got the normal force pushing this way. That means the 2 kilogram pushing back, right? Then you got the N prime, the ground. Then you got the friction force, mu K prime, N prime. And what else? You got its weight, which is 98 newtons. Then you got the friction force, mu s n, pushing down. Okay, so let's do the vertical forces. For in the vertical direction, there is no acceleration, right? So this guy, in the y direction, this n prime must equal what? 98 plus what? Plus this downward force, right? Which is mu s n. So that's going to be what? Mu s was, well, we already know mu s n is 19.6, right? So we can just use that. 19.6. So, oh, which is simply just the weight of this, right? Yeah, because the friction force has to equal to the weight of this in order for it to stay still, right?
Yeah.
Therefore, that means it's almost like as if this guy's riding on top, right?
It's like it's attached to it.
It's almost like it's attached to it.
Yeah, so it's the same bond.
So that means n prime, it has to be like it's almost the same object.
Yeah.
Yeah, exactly. So then you got here 6, 17, 1, 10, 11. So that gives us this normal force, n prime. Then what happens? Now what's happening in the horizontal direction? Then we got in the x direction, you got F minus these two forces, right? That's it. Minus this friction, minus the normal force. Has to equal MA. So what are we solving for? The minimum force required. F min. Okay, what's mu k prime n prime? Okay, mu k prime was the 0.3 between the table and the block, so 0.3. What's n prime? Well, we solved n prime already, 117.6. What's n? N is the 39.2. And the mass of the block, 10 kilograms, right? Yeah, 10. 10. What's the acceleration? Well, they have to accelerate together, right, as a system. So the acceleration is 19.6. So that's the minimum force that you have to exert on the system. You have to overcome the friction force that's fighting you. You have to overcome the force of the block in the front pushing back in order to make the system accelerate at that rate. At 96 plus 39 plus that. What is that? 200 something?
Yeah, that's
270.48 newtons. Huh, interesting. How can we do an experiment to test this? Right? Put the calculator here, right? I'm a little bit scared though, right? Because there's a little bit of friction on the calculator. These rubber things that they put, right? So then go like this, and then push the folder with enough of a force that the calculator stands in place. I don't want to ruin it. You see how it's kind of stood still?
Maybe try something cheaper.
Yeah, something cheaper, like a eraser. You might be able to do with an eraser. Yeah, but once I let go, it goes like that.
You'd have to keep running.
That's true.
Yeah, you gotta keep running with it. You gotta basically keep running with it, pushing. So what's happening is the force between them is creating a normal force, which is allowing the friction to keep it from falling. You see? By me pushing at it, it's causing the force between them to increase. Okay? So now what if you exert 5 newtons less force? You know what? It's good to keep the equations, and then you just have to sometimes change a couple things, and you don't have to redo everything. So B, if F equals 265 point.
I have a question.
Yeah.
I don't know. Keep going.
Yeah, go ahead.
I mean, I don't know if I can do like F minimum minus the friction is equal to the whole system, the mass of the whole system times A. Would that give you the same F minimum? You understand what I mean? Like, not only on big M, but also include small m and
The problem with these kinds of things of just trying to do a whole system is that you forget sometimes about these internal forces like the mu SN, and then this guy pushing back on this guy. I would prefer to do this block by block.
block, like 2 blocks.
Yeah, because then I can see, okay, there's a friction on this guy which is holding it up. Then this guy exerts a force on this guy down, know, when you try to do the system.
Yeah, because I did that. That gives me the same answer because n is equal to small m times a. So small m times a plus big M times a. That's m plus m times a. So that's still, the same.
But how did you do the downward friction force? This guy. Did you do that?
I included
This
that
one.
in.
You might have broken it up like your way, and then you might have done his way. Because I was thinking about it in 60. Because it's like the mass, like the forces on the system horizontally, right?
I don't know. I'll be scared to do that way.
Because I have minimum minus mu.
Sometimes it might work, and sometimes you might.
Mu k prime m prime, which is
But how would you have known n prime is 117?
117 point.
Because the weight of this is just 98.
Oh, I mean m prime is the total mass.
Yeah, but how would you have known that you can treat it as a total mass?
Because it's attached to it. It's kind of like they are together.
Okay, now
It's
you
not
know that.
falling.
Now you know that.
Yeah.
But unless I told you about the internal forces, this guy holding this up, this guy pushing it
I
down.
guess after you
Yeah.
calculate the maximum, like the minimum needed, you could do it his way.
Yeah, I did draw it out, and I know that there is a friction going up for the small block and the friction going down for the big block, and that's the reason why
It's
staying-
acting as if it's attached. Once you do it this way, you can say, oh, okay, there's a shortcut. Maybe I can treat them as being glued together. Yeah, it might work.
Because of the
But it's always best when you first solve something,
Yeah, right.
do it the two bodies separately.
Yeah.
And then you can say, oh yeah, I can treat them, I can now do it quicker. Yeah.
I think the UK prime.
Huh?
I think the UK prime.
Mu k prime, it was given in the problem. 0.7, 0.3, 0.5, 0.2. Yeah.
Because if the question was asked a little differently, then that way it wouldn't work, right?
Well, in part B, it might not work.
Right.
See, if you're 5 newtons less, so what's going to happen if it's 5 newtons less? So then this one will not apply enough force to this, right? And then what's going to happen? This guy's going to slide down, and then so this guy's going to revert to kinetic friction, right? Mu k, and this weight of this guy is not going to change. So what's changing now? This is going to go mu k n.
Bottom one is the UK.
Which one?
The friction.
Yeah, now the friction here changes to mu KL, which means it no longer acts as if, where's the guy? Oh, it no longer acts as if they're glued,
Yeah,
right? In
this
part
case,
B.
you can do that.
Yeah. You see that?
So in the earlier case, we just put it as P, and then we put the P variable in our sum force. But after we found that it was attached, we just assumed that P was just part of the whole thing, right?
Yeah.
Okay.
So now we have here what? What else do we have? We have N, 19.6. Is N still equal to 2A? Yeah, that one's still the same. But no longer is this true, right? USN. So how do we change this part? USN. So now it's going to be 19.6 minus mu Kn is equal to its downward acceleration, right? So 19.6 minus mu Kn, what's mu Kn? 0.2 times n is equal to its downward acceleration, which we're going to have to call A prime, let's say, right? To A prime. So it's accelerating this way, A prime, and it's also accelerating that way with A.
And then they're related because how much force you apply is how fast they'll fall.
Yeah, but here, this is not enough information to do any solutions.
Yeah,
See,
yeah.
before it was. Because how many unknowns do I have here? 1, 2, 3. So I can't solve anything here, right? I just have n is 2a, weight minus the friction equals 2a prime is the downward acceleration, right? So none of this is true then. See? Then I gotta go to the other block and change up some stuff. So now I'm gonna change here F. I'm gonna make it what? 265. 0.48. Is this still true? Mu k prime n prime, 0.3. That's the friction force, right?
Right.
How about n prime? 117?
That's changing.
Oh, that's also changing. Oh, dang it. So now we gotta go to the vertical direction, right?
Right now. Now that one.
Oh my gosh, everything is changing, right? So we have here n prime is equal to what? 98 plus this guy, mu k n, which is what? 0.2n, right? But we don't even know n is, right?
Right. We don't know.
My gosh, so we don't even know this, we don't even know that, so then we gotta take that and put it into here, right? Let's see here. So minus 0.3. So n prime is the sum of these two, you got it? 98 plus 0.2n. How about this n? Well, that n we don't know either, right? Because we don't even know from here. So then we just leave it as n is equal to 10a. Do we have enough equations to solve this? How many unknowns do we have? Our unknowns are a prime, and n, right? A prime, and n. So, but I do have three equations, right? 1, 2, and here's my third equation. So I do have enough equations to solve three unknowns, right? So how do I solve it? Oh, you know what I could do? I could just put n is 2a into here and into here. And that's it. Then we can solve for a first, right?
But it would be a function of the A's, right? Different A's.
Yeah.
Okay.
So n is equal to 2a minus 2a, and then distribute this in. Point 3 times 0.2 times 2, right? We have to multiply all this. 0.3 times 0.2 times 2. That's 0.12a. Right? And then you're gonna subtract these two. And then these two go over to the right side. Then you calculate the A. Yeah, what did I do?
Yeah, should be.
0.3 times 98, it shouldn't be that big.
Yeah.
Must have done Oh, 29.4. Oh, you know what? I think when you subtract them, you get.
You gotta 1, 2, 50.
Oh, what I wrote down is what you get when you subtract. Then you divide that by. You see? So remember what the acceleration was? The system was accelerating when the block was stationary. So now it's accelerating less. Well, that makes sense, right? It was, what was the acceleration? 29, I think, right? So it's 19. Because I'm not exerting enough force. So only dropping the force down by 5 newtons caused the whole huge difference. It went from 29 to 19. Okay, once I get that, then I can get the N, of course. N is 2 times that. Right? And then I can put it here and I can get the A prime. That will tell me how fast the block is accelerating down. So 19.6. Oh, it's pretty fast. I'm surprised it came out that fast. 0.2. Oh, well, because the kinetic coefficient of friction is much smaller than the static, so all of a sudden it dropped, right? So the acceleration downwards is very fast. It's going to hit the ground right away. Which is why it's hard for me to replicate that on the eraser, right? If I don't have the right force, it falls down. Well, then part C says if you exert 5 newtons more force, what's going to happen? Logic will tell you, well, if you exert too much force, maybe the thing is going to accelerate up, or what? Because the problem is saying, what acceleration will the block slide up the block?
Isn't this like one of those molecules out there, like where it's like when the gravity moves up the plane, there's like friction, like you can't have, it can only resist motion and it can't cause motion.
Yeah, I think we had that earlier with the other 2 block problem, right? Something like that. What's gonna turn out that the teacher who's putting this on the test is trying to trick you. He's trying to say, oh, okay, he's trying to make you say the acceleration of the block up the hill is something. It ends up that it doesn't accelerate up. You cannot create a situation where it accelerates up against gravity if you exert too much force. So the answer is the acceleration is still 0. It just stands still. Still.
That would trick us into trying to plug in the mu s instead of, mu k instead of mu s and do the whole thing out.
So the answer is any force greater than 270 will keep the block stationary. It will not move. Will keep block stationary. So there isn't an exact amount of force you need for it to keep it stationary. But then, playing the devil's advocate, you might say, well, why? Because if I exert 6 newtons more force, isn't that going to have a trickle-down effect? If I exert a lot of force here, isn't that going to increase the N?
It just increases the upper limit of the static friction, right? It doesn't really change.
Yeah, but that's
I'm getting a smile because he's hit it bullseye. That's why he'll make a good tutor, because he also understands it very well. Exactly. So increasing this increases the force that this guy pushes on this, which does increase the, right? So this one increases, right? Which means the maximum possible static friction increases, mu s n. Right? So then someone could say, wow, if the maximum possible static friction increases, doesn't that make this guy accelerate up? And the answer is the friction does not have to equal its maximum, the static friction. That only changes what? The way you worded it was perfect.
Upper limit of the static.
Yeah, it only changes the upper limit of the static. It's like you getting today finding out that you have a new job. You get a phone call and your employer says, I'm giving you a raise or I'm giving you a promotion. You have a new position in the company. You go, great. But the employer says, just make sure, just because I'm paying you more, you don't spend it all. You know, you keep the same budget, save that, and use it for some good purpose later, right? So pushing harder is and getting a more maximum friction is the equivalent of getting a new job, right? But the friction says, no, I'm a thrifty spender. I'm not gonna equal the maximum. I'm only gonna equal whatever I need to equal in order to keep this block stationary. How much does it need to equal? 19.6. So the friction says, yeah, it's good that I can earn more and I'm earning more now, but I don't need to spend that. I can still drive my Toyota Prius, right? I don't need to buy a Ferrari. Okay, so what's going to happen? The conclusion is that no matter how much you push, the friction force on the 2 kilogram block will still stay 19.6 newtons. The system will accelerate forward faster, that's true, but this guy will still stay stationary.
So, if we were to like kind of change the reference point, since the force going this way is greater than the force on gravity, we could almost, because you drew it like normal force.
The
right?
force this way
Is
could keep getting bigger, but that has nothing to do with this vertical direction.
Right, right.
Yeah.
But what I'm saying is, like, if we saw it from this perspective, that force is greater than the force of gravity, right? So it would almost be like no matter how fast, you know, what the effect of gravity, that doesn't make me slide sideways if the frictional force doesn't allow me to.
Yeah, exactly.
So if we just, it's a lot.
Oh,
easier
yeah,
to
yeah,
understand,
yeah,
you know what I'm saying?
yeah, yeah.
Like
So
just
you
because I'm
inverted
being
it.
forced upward doesn't mean I'm going to slide sideways.
Yes, exactly.
Okay.
Yes, exactly.
Yeah.
So the object stays stationary.
Yeah.
This problem is a good teacher of it teaches us this huge, big concept that static friction doesn't have to equal its max. It only has to equal what it needs to equal, right? But in the first case, what is the minimum force required? In that case, it does need to equal to its max because you're not exerting a lot of force. You're exerting barely enough force to make it stationary. So at that point, the friction force has to equal its max, right? But once it slides, you exert less force than that. Then we know it slides. Then it reverts to kinetic friction. You see? Okay, now let's apply all of these things we're learning, which is Newton's laws and acceleration, apply them to chapter 6 problems, which is circular motion, dynamics of circular motion.